SEAL, Self-Adapting Language Models. We stand at the frontier of artificial intelligence, where models are beginning to learn how to learn. Welcome to Self-Adapting Language Models, the MIT framework that represents a fundamental step toward recursive self-improvement in AI. This is SEAL, Self-Adapting Language Models, a groundbreaking framework developed by Zweigert and colleagues at MIT that enables large language models to generate their own training data and improvement directives. This isn't just another fine-tuning technique. It's a paradigm shift toward autonomous AI improvement. Overview. The framework operates through an elegant but powerful process. The base language model generates self-edits from context, which are then used to update the model via low-rank adaptation fine-tuning. The reinforcement learning objective is straightforward but profound. Maximize expected task performance. Using the rest to the EM algorithm, SEAL performs rejection sampling followed by fine-tuning on only the highest reward self-edits. This creates a virtuous cycle where the model learns which types of self-improvement actually lead to better performance. Related work. SEAL builds upon but fundamentally advances several key areas of AI research. While previous work focused on synthetic data for pre-training, knowledge updating through weight edits, or temporary test time adaptations, SEAL introduces a novel approach, using reinforcement learning to optimize self-edits that create persistent model updates. It represents the convergence of RL for language models, meta-learning, and self-improvement techniques into a unified, powerful framework. Method. Framework. The SEAL framework operates through an elegant but powerful process. The base language model generates self-edits from context, which are then used to update the model via low-rank adaptation fine-tuning. The reinforcement learning objective is straightforward but profound. Maximize expected task performance. Using the rest to the EM algorithm, SEAL performs rejection sampling followed by fine-tuning on only the highest reward self-edits. This creates a virtuous cycle where the model literally learns how to improve itself more effectively over time. Method. RL loop. The RL loop that powers SEAL follows a clean, iterative process. For each training step, the system samples context and tasks, generates self-edits from the current model, creates an updated model through fine-tuning, evaluates its performance on target tasks, and then uses these rewards to update the model parameters. This creates a continuous improvement cycle where the model literally learns how to improve itself more effectively over time. Method. Domains. SEAL demonstrates its versatility across multiple domains. In knowledge incorporation, the model processes passages and generates implications or restatements, then gets rewarded for accuracy on no-context question answering. In few-shot learning on the ARC dataset, the model takes demonstrations and generates JSON augmentations along with hyperparameters, then gets rewarded for correct outputs on test problems. This shows SEAL isn't just a single trick framework, it's a general approach to self-improvement. Experiments. The experimental setup was rigorous yet practical. For few-shot learning, researchers used Llama 3 2.1b on an ARC subset. For knowledge tasks, QN 2.57b was tested on SQAD with no context question answering. The baselines were comprehensive, including in-context learning, raw fine-tuning, and GPT-4.1 synthetics. Remarkably, all this was achieved with just 2 GPUs in hour-scale computation, making it surprisingly accessible. Results. The results are nothing short of spectacular. In few-shot learning, SEAL achieved 72.5% success, dramatically outperforming the 20% of non-RL self-edits and nearly matching the Oracle upper bound. In knowledge incorporation, SEAL reached 47% single-passage accuracy and maintained 43.8% continued accuracy, consistently outperforming all baselines including GPT-4.1 synthetics. That 40% relative improvement in factual recall represents a quantum leap in model capability through self-directed learning. Ablations. Ablation studies reveal crucial insights. Scaling matters. The 7B parameter model significantly outperformed the 3B version. The type of prompt matters too, with implication generation working best. Most importantly, using the actual task reward dramatically outperformed proxy rewards, and SEAL consistently beat alternative approaches like generative adapters and Integraph. This isn't just working, it's working better than the alternatives. Limitations. Like any pioneering work, SEAL has limitations. The framework shows catastrophic forgetting during continual updates, a challenge for long-term self-improvement. Computation remains non-trivial at 30 to 45 seconds per evaluation, binary rewards limit nuance and learning, and the domains tested, while impressive, don't yet demonstrate scalability to more complex tasks. These are the frontiers for future research. Discussion and future. SEAL represents a fundamental step toward the holy grail of AI, recursive self-improvement. The framework isn't just improving performance, it's learning how to learn through meta-optimization. The future directions are clear: mitigating forgetting through replay or constraints, expanding to domains like code generation and tool use, developing more nuanced reward signals, and of course, scaling. With code available on GitHub, this isn't just theoretical, it's the beginning of a new era in AI development. Self-adapting language models are no longer science fiction. SEAL has demonstrated that models can indeed learn to improve themselves, marking the beginning of a new chapter in artificial intelligence, one in which our creations become our collaborators in the pursuit of intelligence itself.